In the last video, we looked at the necessary and sufficient conditions for minimization of a function of a scalar variable. Here we'll look at functions of a vector variable. Let's consider, for example, this function of the input to this function is a vector of size 2, x1 and x2. So by analogy with the scalar case, the necessary condition has to do with the first derivative being equal to 0. So the first, in this case, it's the partial derivatives df by dx1 and df by dx2. So the common vector consisting of these two partial derivatives is called the gradient of f. Recall from the very first assignment that the derivative of the function f, df of x, is written as df by dx1, df by dx2 in the row vector format. So the gradient is actually the transpose of what we call the derivative. The sufficient condition has to do with the second derivative, as we saw in the last video. The second derivative is a matrix. Again, this is familiar to us when we talked about stability. The second derivative, the energy, was a matrix when the system had multiple degrees of freedom. This second derivative matrix is called the Hessian. So the first derivative is called the gradient, the second derivative is called the Hessian. And the sufficient condition is that the second derivative, the Hessian evaluated at the solution, is positive definite. So for the example written above, the gradient, the vector of partial derivatives, can be computed like this, and setting that equal to 0 gives us x star is the vector 4, 2. Now if we compute the Hessian at that point, the second derivative, we get the matrix 2 minus 2 minus 2, 8. And we can check that this matrix is positive definite. So if you recall, we have a number of ways of checking if a matrix is positive definite. The first is doing a Cholesky decomposition using the function chol in MATLAB. For a 2 by 2 matrix, if the trace of the matrix and the determinant of the matrix are both positive, then the matrix is positive definite. We can also compute eigenvalues, but this is generally not a good idea. It's an expensive calculation for larger matrices. So if we want to solve this optimization problem of a function that takes a vector as input in MATLAB, one way to do it is using the function fminunc, which stands for unconstrained minimization. The way we do that is to create what's called an anonymous function. This is one way to use fminunc, is to create an anonymous function that computes both the value of the function and the gradient of the function. Now what I'm writing here is this anonymous function, and what you should do is look up the help in MATLAB for anonymous functions. I also have a link to the actual code I'm writing here on UB Learns, so you can actually look at the code and try to run it. So we first create an anonymous function that returns the value of the function and the gradient of the function. And then we set up some options that tell the solver that we will actually be providing the gradient of the function to the solver. So that's the option specify objective gradient. We set it to true, indicating to the solver that we are actually providing the gradient. And then we actually call the solver fminunc and say minimize this function f with an initial guess of 0, 0 along with these options. And if we solve, you will find that you'll actually get the same answer, x equals 4, 2, that we got by the hand calculation. So I suggest looking at help for anonymous functions, the function deal, which we are using, as well as the solver fminunc. I've also posted a link to something called an example in MATLAB that minimizes what's called a banana function. That might be useful to explore to see what the different ways of solving optimization problems in MATLAB are. So here is a graphical understanding of what this function is. If we plot this function f of x in 3D, it looks like a bowl, and the 2, 4 point is the minimum point. And then plotted below are contours of this function, which are values of x1, x2 for which the function has a constant